Now, I do think it prudent to understand that Newton's laws are a theory. Are a law. Not theory, I almost blew that. Newton's laws are a law in that they're an observation. There are theories that back up some of Newton's laws. But Newton's laws are a set of rules. And you apply those rules to the universe. Ultimately, these rules can only tell you one of two things. When we apply Newton's laws successfully, they can either tell you an individual force, or they can tell you the acceleration of an object. That's all they can do. As complex as they are, and as elegant as they are, ultimately, that's all they can do. So if your problem says to you, find how far something goes, Newton's laws aren't going to be the way to solve that. Newton's laws might tell you the acceleration, and then with that, you could figure out how far something goes. But Newton's laws themselves will never say it will be here. Now understand, Newton's laws are big in that they explain the natural universe. When I say that, I say the observable universe, what you can see. They have limits. And although Newton didn't respect these limits, it was because of the time in which he was raised that he couldn't respect these limits, because the limits of his abilities to see were a little bit restricted. The three limits, though, not that this will come up in any problem, but I think it's important for you to know what I mean when I say there are limits. Newton's laws are limited because it does not work for the very fast. The very fast. So what do I mean when I say very fast? Well, fast is kind of relative. Speed of sound is fast. That's 300 meters per second. Newton's laws work just fine. Bullets are fast, 1,000 meters per second, just fine. International Space Station, 7,000 meters per second, no worries, just fine. The Apollo rocket on the way to the moon, about 12,000 meters per second, no worries, just fine. In order to get to the limits of Newton's laws, you got to travel about 1% of the speed of light. To put that in perspective, the speed of light, 3 times 10 to the 8th meters per second. That's 3, with a whole lot of zeros, 300 million meters per second. So unless you get to about 1% of that speed, so 3 million meters per second, Newton's laws work just fine. Now, the reason they don't work when you start going fast is because things that are going fast experience time different than things that are going slow. The second hand on a spaceship that passes you going this fast is ticking slower than your second hand is. And because of that, you got to change the rules a little bit. And the reason is because this is a speed limit of the universe. Nothing can go faster than that. Nothing can go that except for light. So it requires what's called special relativity. What's amazing to me, and maybe someday amazing to you, is that Newton's laws still work as long as you provide a small correction. He never imagined that there was a speed limit. Einstein did. When you apply what happens when there's a speed limit to Newton's laws, you can correct them. The correction isn't necessary until you get close to the speed of light. It's called a Lorentzian transformation, but it's just algebra. You can do it with a little bit of trig. It's really straightforward. As long as you know the Pythagorean theorem, you can do the correction for special relativity. Newton's laws also don't work for the very big. What do I mean when I say very big? Well, the Earth is big. Do I need to correct it for that? Nope. The moon is big. Don't have to correct it for that. Jupiter's big. Nope, not really. It's not just big. It's how close you are to something big. So the sun is big enough, but we're far enough away where it doesn't matter. Venus is closer, still don't need it. Mercury is close enough to the sun that requires a correction. Newton's laws don't work for Mercury. And when I say don't work, is if you use Newton's laws to predict how long it takes Venus to go around the sun, no problems, you can nail it. Same with the Earth, same with all the other planets, but Mercury, you're always going to be off by about 6%. 6% doesn't sound like much, But 6% for Mercury's orbit is a couple of hours. And if you're trying to get your spaceship there and it arrives a couple hours before Mercury gets there, you have a problem. So when I say it's not much, it depends on what you mean, not much. In order to correct this requires another kind of science called general relativity. And the easiest way to explain why is big things bend space. They make the shortest distance between 2 points a curve and not a line. Big things, because they bend space, change the nature of time. Time travels slower for things in space that is bent versus things in space that isn't as bent. So because of that, you need to make another correction. Now, the general relativity correction is a little more complicated than special relativity and can't easily be done with just algebra, but can be. It's still an algebraic correction. It is the curving of space. You have to use something called non-Euclidean geometry. You guys have been taught Euclid's geometry. We need to get around that and do non-Euclidean geometry. And basically deal with the fact that we are observing something that's living in a space that's curved. It's hard to understand. It's hard to imagine in your mind, but that's what's happening. So, what do I mean by big? The sun is 2 times 10 to the 30th kilograms. The Earth is 6 times 10 to the 24th kilograms, and we don't need a correction. But, the sun's big. Now, what's that?
Do we know what the exact threshold is between...
No, there is no exact threshold. None of these have an exact threshold. We correct the space station for relativity now to maintain its clock. A lot of satellites do. All GPS satellites are relativistically corrected to keep their clocks aligned. All gravity wells warp space. It's just how much that warping affects your results. So, it caused a 4% disagreement in the orbit of Mercury when we calculate it versus when it's actually there. That's big when you're trying to get to Mercury. Now, that's small when you're trying to get to the space station. We don't have to correct the Dragon rockets for relativity to get to the space station. We can see it, and we can meet it, and we're only off by a little tiny bit when we get there. Due to relativity, that would be something that's unmeasurable because the Earth is not big enough to cause that kind of change. However, we keep time down to a very small, like, picosecond in our GPS satellites, and they all have to be linked together. So at that range, we actually do relativistically correct the time on GPS satellites because it is measurable. It's all perception of how much it's going to affect your answer. Now, this is not true. This one, there's a threshold. So you'll like this one. I hate this one. The very small. Newton's laws do not work for the very small. So when I say small, I'm talking picometers. And sometimes femtometers. So when I say that, I know you don't necessarily know what they are. Pico is times 10 to the negative 12th, and femto is times 10 to the negative 15th. So Newton's laws work fine until you get down to about the size of an atom. They work fine between atoms. They work fine when you compare one atom to another atom. They don't work fine when you attempt to explain why electrons do what they do around the outside of an atom. Just to give you an idea, this. Raise your hand if this looks in any way familiar. See them? Yeah. We love this stuff in chemistry. Isn't this where you had to do the blanks and do the up arrow and down arrow, up arrow, down arrow, up, and then down, and then, do you remember that? The orbital diagrams? Yeah. Each one of those corresponds to a different energy level. And Every single atom has a similar structure, but the energy levels around all the atoms are slightly different because the atom size is different. If you try to apply the ideas of Newton to how the electrons move around the atom, you will fail. Who remembers the word Rutherford from chemistry? All right, so Rutherford is the first guy to realize there's a nucleus. He attempts to apply the rules of Newton's laws to explain the energy levels of the electrons, and it fails. In fact, you can't do it. It doesn't explain it at all. What was found, and this is where it gets weird, is that the electron instantaneously jumps from one energy level to the next and never exists anywhere in the middle. Do you remember looking at those light boxes and seeing the different stripes from the different kinds of lights? Like when you put hydrogen out there or you put neon out there and you look through the box and see the light stripes, it's spectroscopy for light. Well, that's actually telling you the specific changes in the electrons. What is not really talked about in chemistry is that the electron doesn't move from one level to the next. It instantaneously changes location. So either it doesn't exist for a second, or it exists in both places at once, but it never exists in the middle. It can't. It's impossible for it to. Now, I don't know why. Well, I took 2 years of figuring out why, called quantum mechanics. But, yeah, Ant-Man. It is not Ant-Man. Everything, I love the Marvel movies like the next person, but there's no quantum realm. Quantum mechanics is a set of theories trying to figure out why the energy levels are the way they are. They don't explain why the electron does what it does, by the way. It's a theory, but there is fact that you can look at the energy levels and measure them. We don't actually have a law here because this stuff is weird enough. This is applying a set of statistics to a wave function, and it creates specific energy states. It is incredibly successful at predicting the structure of the atom. But there is nothing about Newton anywhere near there. This is not a correction to Newton. This is not massaging Newton to fit. They've thrown it all away and created a completely new set of mathematics and dynamics to explain this. And even now, after 2 years of it, it was like a terrible fever dream to which I could not wake up. It was horrible. And I will never take quantum mechanics again. I have spent basically the last 25 years specifically forgetting everything about quantum mechanics. The books are over there laughing at me right now on my shelf, and I intend to never open them again. So, the 3 places where Newton's laws don't work. I want you to know from the big picture that Newton's laws are about forces. At least in a grand scape, it's a law about force. Somebody tell me the childhood, elementary school definition of force. Say again?
Pushing something?
Push or? That's right. A force is a push or a pull. That's all a force is. What Newton's law states about forces is that the only way you can change something's motion is by applying forces. That the natural state of an object is to have no acceleration. I know you're not writing that down, but you should. Because that is all there is. That's it. That's Newton's laws. And we're going to learn more than that. But if you understand that statement, you've got 50% of all of physics. I'll say it again. Yeah, I'll say it again. Then, the only way to change an object's motion is through the application of a force. The only way to change something's motion is through the application of a force. The natural state of an object is to have an acceleration of 0. Now, you have to understand something. I'm being very particular about what I'm saying here. The natural state of an object is to have an acceleration of 0. This doesn't sound like much, but look at all the objects in the room. It's very unlikely that they're moving, even in your room. And I see some ceiling fans, but in general, most of the objects in your room aren't moving. Up until this point, the Greeks and their view of motion was that things had impetus. You could give something impetus, and it would use that impetus until the impetus ran out, and then it would stop. Their view is the natural state of the universe was to be at rest. Notice I never said anything about whether the object was moving or not. I said the natural state of an object was to not have an acceleration. That doesn't mean it can't be moving. In fact, Newton would say that the natural state of things is motion. That if you give something a bit of energy, it will stay moving forever unless something else causes it to stop. Now, this was hard to observe because everything on the earth, if you throw it, it eventually stops. And so a lot of people did not accept this idea. He had to fight and prove for it to be true because there was no place on the earth where you could observe an object going on forever. We, on the other hand, now understand a little more that there are forces that act that you can't see. And because of that, we tended to ignore them because they were invisible to us. In fact, there's lots of forces you can't see. But we now have a broader understanding that forces cause changes in motion. But the natural state of the universe is to be in motion. So something moving isn't interesting. When something's movement changes, that's when something happened. That's what you look for. Anytime an object's motion changes, there was a cause, whether you can see that cause or not. That's the big implication. Anytime an object's motion changes, there had to be a cause, whether you can see that cause or not. It will be your job to figure out what the cause is. I will tell you that something's motion is changing. You need to figure out how, why. That's what I said when I said Newton's laws are about finding a force or determining an acceleration. I didn't say you never know what force it was. I'm going to help you by determining what these forces could be. There are lots and lots of different forces to talk about. We will break them up into three broad categories. And in these categories, I will tell you from the beginning that there are 4 in the first category I'm going to talk about, and 2 in each of the next 2 categories I'm going to talk about. I'm going to talk about them backwards. So I'm going to start here with resistive forces. Then I'm going to talk about contact forces. And then I'm going to talk about fundamental forces. But in your notes, you need room for 4 different fundamental forces and some information about each, 2 different contact forces and some information about each, and 2 different resistive forces. However, just know from the onset that these are like checkboxes. When we start analyzing what's happening to an object, we will ask ourselves which of the fundamental forces are likely acting in this situation. Are there any contact forces acting in this situation? Is there any resistive forces acting in the situation? We will go down this like a set of checkboxes, trying to narrow down what's causing the effects that we see. So, resistive forces. Generally, a resistive force is exactly what you would expect it to be. Anything that tries to prevent motion. That's a resistive force. Any force that attempts to prevent motion. I know that's pretty easy a definition, but that's what it is. That kind of suggests something, though. In many cases, the object has to be moving to experience this force. It's trying to resist that motion. We'll talk about 2 different kinds. Friction tries to prevent sliding. Notice I said tried to. I didn't write tried to. You should write tries to prevent sliding. It can act when things aren't sliding or when they are. You already know that. You know that because every time you walk, you hope your foot doesn't slide. But let me tell you, the ground and your foot, they're trying to slide apart. And some of you have discovered that because sometimes your foot does slide. And those are bad days for you. because there's almost always a witness. There's also drag. Drag is a force that tries to prevent an object from moving through a fluid. Drag is a force that tries to prevent an object from moving through a fluid. Drag is a force that tries to prevent an object from moving through a fluid. Like air resistance, viscosity. These are all drag forces. So a force of drag is acting on an object that's moving through a fluid. You have to be moving through the fluid to experience drag. This force is always against that motion. It's trying to stop you. In general, resistive forces try to take energy away from an object. We'll have a discussion about energy all year long, and here's where it's going to start. All of these forces attempt to take away energy. Contact forces are just that. They are observable. That's right, 10 o'clock, time to mow the lawn. They are observable. You can see them because they require contact. The object has to be touching something in order to experience a contact force. But it's bigger than that. Anything in contact with the object imparts a force. Anything. More importantly, everything in contact with an object imparts a force. Your butt on the chair, your arm on the table, your pencil on your paper. There's forces at every one of those exchanges. Anytime you are touching something, a force is being imparted. We will break it into two categories: normal forces and tension forces. Yeah, get out there and mow that lawn. You guys can't hear it. You guys at home, but that riding mower is right outside my door right now. They're getting on it. They're making that grass shorter. What I've never understood is why they mow the lawn during the school day. Why? They get here at 6. They can mow at 6 a.m. They're here till 4:15. They can mow at 4:15. But they insist on mowing the central area in the middle of the campus every time, Tuesday or Thursday at 10 a.m. Makes me crazy. I've been here for 16 years, and they always do it in the middle of the day. Why not Saturday? Why not Saturday? Nobody here on Saturday. Anyways, normal forces and tension forces. They're pretty straightforward. Normal forces are pushing forces. Now, they're not called normal because they're ordinary. They're called normal because they are perpendicular to the surface. You will screw this one up. Don't. I'm telling you, you're going to screw this up. But no matter what, the normal force has to be perpendicular to the surface in contact. No matter what you think is happening, normal forces can only be perpendicular to the surface in contact. Period. Now, just to add to that a little bit, friction prevents one surface from sliding past another. So there is no friction unless there's a normal force. If you can read between the lines and make that connection, you should understand that if there was no normal force, there won't be a frictional force because there's no surface in contact. So don't put it in your answer that friction is acting if the object's not touching a surface. Tension requires a string or a cable or a cord. Do I have to keep going, or do you get the idea? Tension is a pulling force. It requires some connection to the object that allows it to be pulled. So cables, conduits, strings, ropes, pick your thing, but tension requires a connection. And it's a pulling force. It can act in any direction. Now we're going to end by just introducing the concept of fundamental forces. These forces are the result of fundamental forces. In fact, all forces are the result of fundamental forces. Now, to be clear, fundamental forces are supposed to be called fundamental interactions. and they share something important in common. That the fundamental interactions occur without contact across distances. They are invisible. They are magic, for lack of a better term. We have no theory that explains why they exist.
What's that first word? Interaction?
Without contact across distance. There are 4 fundamental forces. You already told me one of them earlier today. When I asked you why the pencil fell, you all said gravity. Gravity is a fundamental force. It is a force of attraction between objects with mass. It is a force of attraction between objects with mass. And with that, we end today. About the fundamental forces. And I spent way more time on this in first period than I'm going to spend in this period. I just want you to know a couple basic things about the fundamental forces, and I'm not going to write all of those things down. I am going to write down that there are 4 fundamental forces. There's the gravitational force. There is, hold on. Well, it's that. I got something stuck on my nose. I think it's in my mask. Like, I didn't trim my nose hairs enough, and they're like getting all in with my mask. And I know that that's like totally TMI, but you know, when you get old and you know things are starting to happen, the nose hair mask problem is a real thing, and it's being covered, you know, in the news media. It's an issue. I know. And I have these huge masks because I have to wear it all day long, and the little ones, I think I chew through them by the end of the day. So, all right, 4 fundamental forces. Starting with gravity, then there's the electromagnetic. See, the mask jokes don't go over for the people at home because they don't have to wear them. They get to free face it. Free face. Free the faces. Yeah. There's the weak nuclear and the strong nuclear. These are the 4 fundamental interactions. I want you to understand that the fundamental interactions are actually the only way that energy gets exchanged in the universe is through this. The only way we know that the universe exists is through these interactions. These are the 4 things that control all of how the universe works. And we don't know anything about them. And we really don't know anything about them. We have some things about them that we have discovered, like they all act without contact. That's important. They act without contact, which is why we don't really know anything about them. We don't know how one thing is aware that the other one is there. Like, how do you know which direction to fall? Like if you trip or if you drop something, how does the thing you drop know where the earth is? And I know it sounds ridiculous, but the truth is, it's not like when you drop a book, the book is aware that down is in a certain direction. It's a book. It doesn't know anything. But it falls downwards for some reason. What makes that happen? Some people think that the book is aware of the earth because the earth is sending it particles. And that's how it knows. This is the particle exchange theorists. They think that the book and the earth are exchanging graviton particles. And these particles carry information about the force that connects these 2 objects together. It sounds like total BS to me because it doesn't even sound like a real thing. These are massless, odorless particles that convey information about force. But there's a whole group of scientists attempting to find the graviton particles. And they believe all of these forces are connected together by these particles, specific to each force. I don't buy into that. I'm actually a field effect theorist, which, and not that that's a real, like I'm out there studying it. I just teach high school physics. I'm not very important. But I will say that what I mean by that is I believe that these objects change the nature of space, and that's why things fall. The example I give that's the best one is that you put a bowling ball in the middle of a trampoline, and other things will fall in towards the bowling ball. You got that mental image? I think that's what the Earth does to space, but in 3 dimensions. That the Earth makes a big dent, and everything falls into the dent. That's what my brain does. That's what my brain thinks is happening. But the truth is, nobody knows. It's a mystery. And these theories, every one of them has problems. And they get weirder as you consider what some of these other forces do. So nobody knows how they work, but they work without contact across great distances. And that's the important detail. So there are 4 of them. I want you to know these things about them. They get stronger as you go this way. Gravity is the weakest. Strong nuclear is the most powerful. When I say that nobody knows what these things are, I really mean that, because when I went to school at your age, there was a weak nuclear force. When I went to college, there was no longer a weak nuclear force being taught in schools. They just said it was part of another force. And then when I graduated college and had been teaching for 3 years, they brought the weak nuclear force back. Now, I am not so terribly old, and that whole thing was in a span of like 12 years. So it's not like, we really know or have a handle on this. We are always changing it. But I do want you to know this, that all of these forces act on specific intrinsic properties of matter. The word intrinsic is probably not in your SAT notes for like what words you're supposed to know, but it's an important word. I like that word. You'll sound smarter if you use the word intrinsic. Intrinsic means to be a part of the nature of something. That's what the word intrinsic means. Like, to be a bunny rabbit is to have long ears. It's an intrinsic part of being a bunny rabbit, if you're into bunny rabbits. And if you're into bunny rabbits, something probably is wrong with you. But we would say that perhaps a shell is an intrinsic property of being a turtle. So when we talk about intrinsic properties, they are like the nature of something is to have that property. So each of these forces acts on an intrinsic property of matter, a specific property that matter may have. For gravity, that's mass. Gravity acts on all things with mass. It pulls them all together. It is an attractive force only. The electromagnetic force acts on charge. You learned about that in your chemistry class. There's 2 kinds of charge. They come in 2 flavors. And the flavors could have been chocolate and vanilla. I would have been happier if they named it chocolate and vanilla. Instead, they named it positive and negative to make it sound like it's mathematical, but that's ridiculous. It's not. They just needed 2 different types because there were 2 different types of charge. There's a lot of things that have 2 different types, and in the nuclear world, they got at least a little bit interesting because they called them up, down, top, bottom, and strange charm. So, but with charge, all we got was positive, negative. So the least interesting people came up with like the labels for charge. The reason why there are 2 different kinds of charge is so that we can have the possibility of both attraction and repulsion. Now, I'm not sure why that is. I mean, I didn't make the universe, but I will say that that's how we differentiate whether there's going to be an attraction between 2 charges or a repulsion. What's important to understand is the electromagnetic force is the only force that repels. It is the only force that pushes things apart. Every other force pulls things together. I can't tell you very much about the weak nuclear force because although I've read a lot about it, I really don't understand it. The weak nuclear interaction is the interaction that causes radioactive decay. I don't really know what it's doing or what it's acting on. My suspicion is that we don't understand it, and so we just provided a name for it, and that what's happening is more complicated, and we're still studying it. We know that it does a few things, like it is trying to drive an atom to be more stable. For smaller atoms, it's driving it to have equal numbers of protons and neutrons. For bigger atoms, it's keeping the protons from fighting, more or less. But basically, it's trying to create a more stable nucleus. The strong nuclear force acts on nucleons, protons and neutrons. It binds them together in the nucleus. So it won't act on things like electrons because they're not a nucleon. It's not found in the nucleus of an atom. So the strong nuclear force can't pull an electron. The thing about these forces is that they can only act on the intrinsic property for which they are managed. So the electromagnetic force can't act on a neutron because a neutron has no charge, therefore it's invisible to that force. You can't pick up a neutron and grab it with that force. You'd have to use something else. And that's the whole thing about all of them, is if you want to manipulate matter anywhere in the universe, you need to be able to push on it with one of these forces. But if that matter doesn't have that property, you can't grab it. Neutrinos are like that. We can't grab them. We can't touch them. We can't move them. We don't know what intrinsic property controls them. None of them, apparently. So they simply pass right through. Everything else, we have found a way to get a handle on it. But there are bits of matter that we can't get a handle on. The range of these forces increases as you go this way, with the gravitational force and electromagnetic force having incredibly long range, light years, but the strong nuclear force only acting in a very small distance, femtometers, like 10 to the negative 15th meters. But when I say that they get stronger as you go from the top to the bottom, gravity is the weakest of the forces. It is really, really weak compared to the electromagnetic force, which is several orders of magnitude bigger. Orders of magnitude, not twice as big, several hundreds of millions of times bigger. And the strong nuclear is several orders of magnitude bigger than the electromagnetic force. So you have to think about this for a minute. All of these are about energy. So if you want to power a city using gravity as your energy source, the only way to do that is to probably get water going over a dam. That way you're using gravity to pull the water across. It takes hundreds of millions of gallons of water to power a city for a day. Now, if you want to switch to like natural gas, it probably takes maybe a couple hundred gallons of natural gas to power a city for a day, because it has that much more energy associated with it. Now, if you wanted to use like strong nuclear as your fuel, anybody have one of those keeps it cold for 48 hours bottles? You guys know what I'm talking about? I don't know what they're called. They're the... Okay. If you have one of those like bottles and you're carrying around your water in it, that would be enough fuel to power that city for about a month. That's how much energy is there if it was pure nuclear fuel. So when we talk about like the amount of energy associated with these things, it's not a little difference when you go from one to the other. It is massive in the amount of this energy you have. Okay, so all of the forces, we will only deal with this one. Although I want you to know that, like these are multiple choice questions. When it comes to actually using these rules, we're only going to use the top one. And we call the force of gravity on an object its weight. Not its mass. Its mass is something that is about it. Its weight is how the object behaves when it's in a gravitational field. And weight is a force. All right. A couple things to say about force that you probably already know, but I have to put this into your perspective. I want to talk about weight as my example. When we calculate weight, it's pretty easy to do. We take the mass of the object and multiply by the acceleration of gravity. Please note that on the Earth, that's just going to be mg. We're going to use probably 10 for this most of the time. But also, that suggests that the unit of force is the kilogram times meters per second squared. That is the unit of force. Almost all of our units are complex units. We will only have kilograms, meters, and seconds in all of our units. But I'm just going to write down the first semester units. These are some of our first semester units. And you have to know what each one of these goes to. Now, they're all very similar. You do see that, right? And that's going to make you crazy. What's worse is they all have names. Like this one, it's called the Newton. That's the unit of force. This one doesn't have a name. This one is the joule, the unit of energy. This one is the watt, unit of power. And this one doesn't have a name. So some of these have names, and some of these don't. But all of our units in this class look like this. They're all some kind of combination of kilograms, meters, and seconds. That it will make you crazy. Having like a decoder key for this, not a bad idea. That little note card that's got all those equations on it, maybe put the decoder key next to it. For the time being, we only have this one. But a joule, we will say, is a Newton meter, and a watt is a Newton meter per second. I mean, they get really complicated when you start looking at them. We start mixing in their different things. So I would encourage us to be aware of units, because units were really easy when it was just meters and seconds. But now, whole new thing. So, what we're going to do, and this is, like I said, first period is an indicator. They thought, wow, this is really going slow, Mr. Shelton. You're really, 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 going very slow and deliberate. Yep. I'm going to split this up, and I'm going to have a series of steps on this side and examples on this side. And we're going to do an example question, but I'm going to tell you how we do these kinds of problems. And the set of steps that's going to be on the left side is the same set of steps we'll have for every one of these questions. Now, to understand this, you have to understand that we are going to be talking about Newton's laws. And just to put it, let's get back to this. Our set of steps starts, step 1. Is it a first law or a second law problem? That's our first step. We're going to try and figure out from looking at our situation whether we apply the first law or the second law. I want to tell you that as a set of steps go, you might not be able to determine that. You simply might have to take a guess. If you have to guess, always assume second law. It's always the safest one. So if you don't know, always assume it's a second law, not a first law. Now, I'm setting up a situation over here so that we all have it together. I'm going to set the simplest one I can, a book on a table. That's going to be the example we're going to use. Book on a table. So, as examples go, do you think this is going to be a first law problem or a second law problem? Yeah, I think we're going to say first law. Book on a table likely just sits there. So we'll start by assuming it's a first law problem, which means I think the net force is going to be balanced. So if you look at a situation and you can't tell, you have to assume it's a second law until you can prove it's a first law. All right, that was step number 1. Step number 2, draw a free body diagram. You are going to love to hate this. Draw a free body diagram. It is the part of this that takes the longest. It's the part that I am the meanest about. It's the part that I think you guys need to be great at. And it was a thing that I told every student last year was going to be on the exam and wasn't because of the pandemic. They couldn't draw one. But every year before that, we always have to draw a free body diagram. You will be rated on your free body diagram. So there are a series of steps when it comes to drawing a free body diagram. You must be a master at it. Here's where your colored pencils and your rulers come in, because I want the lines to be perfect and I want your drawings to be clear. So we'll start with this. All free body diagrams begin by reducing every object to a single dot. Every object becomes a dot. Basically, we ignore the object's spatial size. So over here, the only object I have is the book. And so I will reduce the book to a single dot to begin my free body diagram. Now, the next thing we're going to do is we're going to draw an arrow representing each force. Now, to do this, we're going to go through our check boxes of different categories of forces. And there will be 4 check boxes here. I know we only had 3 in the list, but trust me, there's a 4th one we didn't consider. So we'll start with fundamental. Are there any fundamental forces acting on our box? So what we're really asking, is gravity acting on our box or our book? So the answer is yes. So we start with gravity for a very important reason. Gravity is going to set the tone and scale of our diagram. We generally base the size of the other vectors on the gravitational vector because we tend to know more about the gravitational vector. So we draw a single arrow straight down, but we're going to use this one as our reference for size. Every force must have a label to indicate which force it is. I use a capital letter consistent with the name of the force. Adam?
Should we do this right over the diagram, or does it not matter?
Your free body diagram will have to be separate from your picture of the book and such. But in the future, I will almost always do it right on my diagram.
Okay.
But on the exam, they usually provide a box for you to draw your free body diagram in. Now, your textbook, they label different. They use a capital F with a subscript of the name of the force. I think that is, I don't like that. I just don't like it. Because, and I know it's nice because they all say F for force, but I just don't like it. So I will just use a capital letter to indicate the type of force we're talking about. All right, once we've covered all the fundamentals, and we will only have gravity in here, next, our contact. So we're looking for our surfaces, and we're looking for strings and ropes. Clearly, the book is in contact with the table, so the table imparts a normal force. Now, the normal force must be drawn perpendicular to the surface. So I don't think that's hard to do here. It's pretty obvious, but I'm going to draw an arrow that is perpendicular to the surface. And since I know there's no cables or ropes or anything, I'm kind of careful to draw that arrow so it's the same size as the weight. Looking ahead, I don't see anything else that's going to be acting on the book to keep it from falling to the floor, so I think it's the normal force that's preventing that. So I'm going to draw the normal force in such a way that it balances the weight. I don't know that for sure, but I'm trying to make my drawing consistent with what I think is happening since I started the problem believing that the forces were balanced. Now, we're going to keep going through the list, even though I don't know if there is another force here. The third force would be resistive forces. Like, do I believe friction is acting on the book? Is the book trying to slide off the table? Then yes. If the book doesn't appear to be trying to slide off the table, then probably not. I think if it's a level table, there's probably no friction acting on the book. The fourth one, though, and I didn't make this a category, but I do want you to see it, is the fourth idea is they could just tell you there's a force. I'm going to call it applied forces. They can tell you in the problem that something's happening. There's a force on the object to the right. It doesn't have a specific category, but if they just indicate that there's a force acting, you have to put it in there. All right, so we've gone through all of our check boxes. We've checked off every one of them. We've considered all the forces. Part C. Draw a coordinate system. This finishes your free body diagram. Now, this part is not as easy as it sounds, and I want to be very clear. You have 3 priorities, meaning there are 3 things you should consider in drawing your coordinate system. First, if it's accelerating, line up the positive x direction with the direction of the acceleration. I'm not going to write this down. You should write it down. Under draw a coordinate system, there are 3 priorities. Priority number 1, if it's accelerating, draw the positive x direction in the direction of the acceleration. Makes your problem easier. If it's not accelerating or you don't know, then draw the positive x direction in the direction of motion. If you can't use that priority, your last best hope is to draw your coordinate system aligned with the most number of forces. Those are your three priorities. Direction of the acceleration. If that doesn't work, the direction of motion. If that doesn't work, the direction that lines it up with the most number of forces. This object's not moving, which means I'm going to use the last priority, which is to line up my coordinate system with the most number of forces. So I'm going to line it up with the only two forces acting. But you always draw in a two-dimensional coordinate system. Now, I will force you to do this. You need to go through your coordinate system and label positive x, positive y, negative x, and negative y. You must identify direction. All right, that is how to draw a free body diagram. I know it doesn't seem like much, but to me, the diagram is the most important part of getting this right. Which brings me to step 3. In yellow, because you don't always have to do it. Resolve any off-axis forces into component vectors. Any force that isn't directly along the x or y direction is considered an off-axis force. Any force, and you guys are writing these things that I'm saying, right? Because I'm not going to write every little detail down. I'm giving you the banner points. You guys should be following up. Any force that is not directly in the x or y direction is off-axis. You need to do the trig to come up with its components. Lots of students fail here miserably. But this is why we went with our trig already. So any force that's not in the x or y direction, you have to do the trig to convert it into component forces. And I didn't spell the word component right, so you should not copy that down exactly like that. You should let me write the word component correctly. Component. There we go. Now, once that's done, we are quite literally at the end, because step 4 is apply Newton's law. Now, applying Newton's law is not hard. Once you reach this point, you just follow the instructions. The instructions stated in Newton's law to add up all the forces in your system and set them equal to, in this case, 0. So I am going to apply Newton's law by following those instructions. I'm going to look at my system and add up the forces. There are two forces. There is a normal force and there is weight. I'm going to take into account their direction. Positive for normal force, negative for weight. And I'm going to set them equal to 0. That is following the instructions. So I will apply Newton's laws. Newton's laws is a set of instructions. I will follow the instructions. And what I get when I'm done is a custom equation that can be used to solve my problem. Listen very closely. Newton's laws create a custom set of equations. One for the x direction, one for the y direction, and one for the z direction. They create a custom set of equations that can be then used to solve your problem. Which means that every single Newton's law problem is going to create a custom set of equations. We're going to see lots of examples, but don't assume that I can't create an example you've never seen. You need to come to every example as if at the end, I will have a custom set of equations that will solve my problem. That's what's going to happen. At the end, you'll create something new that hopefully you can use to figure out the answer to the question. What we did here, there was never a question. I never asked you what we were looking for. We are analyzing a situation, but at the very end of that situation, you will have an equation that can be used to solve your problem. Now, I can't a point on that. There are only two laws. There's the first law, and there's the second law. Since the first of our steps is about which law to use, I can tell you right away that the two laws are actually the same thing. There really isn't a difference. The first law covers all static cases, and the second law covers dynamic cases. Now, that really doesn't mean very much, so let me make it very clear. Static cases is when the acceleration is 0. Dynamic cases is when the acceleration isn't 0. So what's a static case? A case where an object at rest, or an object at constant velocity. Dynamic is when an object is accelerating. Now, be aware, I am going to try and trick you here. Constant speed is not constant velocity. If the light turns green and I go to make a left turn and I go through the intersection at a constant speed of 12 miles an hour, but I'm turning left, although my speed is constant, my direction isn't. I am accelerating. Do not confuse constant speed with constant velocity. Guarantee I'm going to put that on the test in the multiple choice and you will screw it up. So look for situations where the object's direction is changing. That's an acceleration. Anytime an object's motion changes, it's an acceleration. And that's a second law problem. The law looks like this. It's a summation with the F, with the bar, and a 0 here, and a summation, F with the bar, and an MA here. These are Newton's first and second laws. And they are really the same law, because it's this law, but with a 0 for the acceleration. But I want to be very clear what these laws are. These are not equations. They're instructions. And you have to treat them like instructions. Because our first step in solving a problem is trying to decide if it's a first law problem or a second law problem. So we're looking for clues about whether it's a first law or second law problem. This law is about balance. And this law is about unbalanced. The law both can be read right to left or left to right. I drew those in the opposite direction than I was saying them. I know, impressive. Nobody really noticed that, but that was very impressive by me. Not that it matters. It doesn't. Let me explain how you say these laws. Let's start with the top one. It says, if I add up all the forces, that's what this symbol means, to add up. If I add up all the forces, taking into account their direction, that's what this symbol means, and they are balanced, then the object's motion won't change. That's what that law says. If I add up all the forces and take into account their direction, and it is balanced, then the object's motion won't change. That's what the rule says. Now, that rule can be stated in the other direction. If I'm observing an object and its motion is not changing, then the forces must be balanced. That's reading it from right to left as opposed to left to right. So if I look at an object and its motion is not changing, then the forces must be balanced. Even if I don't think they should be, they must be. That's the law. Now the second law is the same, except that it deals with what happens when it's unbalanced. If I add up all the forces and they are unbalanced, then the object will accelerate. That's what this is saying. But here's the clincher. The amount of the acceleration is dependent on its inertia. This is not mass. This is inertia. It's actually the most important part of this whole page. You see, Newton recognized that inertia was the biggest and most important idea here. That it is inertia that determines how objects respond to force. And their inertia is what dictates how they move. The word inertia means resistance to changes in motion. That's what the word means. Resistance to changes in motion. We can measure it through mass. But the only way to actually measure inertia is to push on an object and see how it accelerates. That is the only way to actually measure it. We use gravity to help us measure that when we're on the Earth, but trust me, when you're in space, you can't do it that way. The only way to measure something's inertia is to push on it, to apply a force and see how much it accelerates. Now understand, I think you know this. Big things are hard to move, small things are easy to move. That's the essence of inertia. So sometimes a force is really, really effective because the object doesn't have much inertia. And sometimes that very same force is less effective because the object that it's acting on has more inertia. This idea is how you're going to pass your next test. Because these sound so obvious. Like I'm telling you, like I'm reading the ingredients on a food box, but they are subtle. The effectiveness of a force is dependent on the object's inertia.